Alright, so I'm working on this right here. I'll show you what that is in a second. So here's Walter, obviously. Walter has two sonars in the front, but for argument's sake today, we're going to consider both of these sonars to be one sonar. This one scans from 90 degrees out to the side and scans to the forward position. At that point, this one starts in the forward position and continues scanning to the other side. So we have a 180 degree arcing sweep as if there was one sonar in the center. Alright. Now, there's a total of 88 counts, 89 counts actually. So just basically 90 degrees in, or 180 degrees in 2 degree counts. So every 2 degrees, dunk, 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 the sonar is going to fire off and take a reading. Now, those readings are shown here. This white dot is Walter in the center, alright? And the distance from him going out in a ray, there's rays every 2 degrees going out, is the distance that the sonar has fired. This is to scale. Now, anywhere there's a blue line, it means that the measurements have not changed very much from the last reading it took. But where there's a red line, that shows a large change, a substantial change. So, so we're going to consider the blue areas paths, and we're going to consider the red areas edges. So, like for instance here, now I know it's technically these are obstacles, but even if the sonar is seeing infinity or the far wall on the other side of the room, it's still going to see something. So the first thing we're going to do is we're going to establish these sections called paths. And each one of these sections called a path is made up of various rays, going out from the sonar. The more rays in a path, the wider the path. All right. And then also, just as a quick note, Grog pointed this out to me, and it's a really good idea, that these reds, I consider this guy here, which is almost, sort of a 90-degree corner. Well, if we were looking at this corner, the blue is the wall we can see, and the red is, could be something interesting. Like, if we were to travel this direction and look around this corner, in the future, when I'm deciding on what path to take out of the available ones, I might consider these blind spots, because if this was really long, if there was an edge here or a wall here and a really long guy here, then we assume that this is a wall and like a hallway, like a corner or something. But something there's a lot of around the corner and back there somewhere that we don't know of, but we know it's there based on, there's probably an edge here and then a long thing we don't know about and an edge here. So we might want to head over. We might be curious about that long edge. But at any rate, so all this gets stuffed into array after array after array after array, and it comes out like this actually. These, and this is all in the post. Each one of these is an array kept in an array list, and it's showing all of the distance, measurements. So index 2, that's the second section, and where's my finger? There. These are the distances taken at each of those rays. So each one of these numbers corresponds to a ray and the length of that ray. Okay, so after we get through all of those and we crunch the numbers, we get down to this. Total number of available paths is 6. And so we have 6 pathways here. 1, 2, 3, 4, 5, 6. Okay. And this is going to start at ray 0. And so if we go here, the first path is 7 rays wide. So that would be 7 readings wide there. The next path is 33 rays wide. I'm sorry. No, I'm sorry. This is the last number of the path. So this would be reading 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 33, And then the next one ends on number 39, so that point right there is 39, that point right there is 59, and then because we have the last number of each section, we can then subtract and do some math, and we can figure out our width. So here, path number 1 is 7 clicks wide, so that is 7 clicks wide. The next path here is 26 clicks wide. Next one's 6. Next one's 6. This one here is 20, 16 clicks wide, and 13 clicks wide. And then again, like I said, we can make a decision on which path to take based on a lot of variables. But just for simplicity and for right now, I'm basing it on the widest path. Eventually, it's probably going to be the one that's farthest away, or... Oh, no, actually, I have both. I have both. Okay, so right now, we take these widths, and we bounce them off of a minimum, a threshold, basically, and we come up with path 2, 4, and 5 are wide enough to drive a robot through. So if you look at here, this path here is wide enough for a robot to fit through. This path is wide enough, and this path is wide enough. Or wait, 1, 2, 3, 4. Sorry, that one, and that one are wide enough to drive a path through. So those are our available paths that we can choose from. And then we go to our next step, which is the widest path. The widest path is the second one, obviously, that the robot spit out, or the processing spit out. And then the oh yeah, I'm sorry, I'm looking at my notes now. I haven't coded the farthest one away yet. That'll probably be my next thing to code. And then what we do is we calculate the center point of this path, and then we add it to the length of the paths preceding it. In this case, we have, I guess it's just the first path, 7 plus half of the width of the second one. 13 plus 7 is 20. So 7 plus 13 is 20, multiplied by 2 because these are in 2-degree segments, and that leaves us at, chosen heading is 40 degrees from left edge. So if you consider this 180 degrees around, and that's 90 degrees, then about 45 degrees is right there, and my code is telling me 40 degrees, so we're right there, 40 degrees, which is perfectly centered in the widest path. And then again, since this is Walter's always facing forward according to this because his sonars are on the front. Now he just needs to calculate to turn 40 degrees or 50 degrees off of the center line to that heading, and bada boom bada bing, he is heading for an available pathway that is, in this case, the widest. But again, when he, with just a little more coding, can choose, like again, we know that these paths are wide enough for a robot to fit through, so we have these to choose from, and then we can go the one that's the farthest out, the one that's the widest, the one that is wide so far out and also has the longest amount of unknown interesting space, which is these blind corners, these red ones. And so so there's my proof of concept, and there is what I've been literally working on for the last year that has just come to fruition right now. Not to mention, all of this data is being stored in array after array after array, and this particular drawing is being drawn to a buffer, not the actual window, not the actual sketch window. So because it's a buffer and I can save these as buffered images, I can actually take these measurements every so far as I go, and then I could even, well, I can go through and check, review the data, but I could also play them back in succession, like a flipbook, and you can see this this pathway, this obstacle line, morph as Walter drives around. So so there you go. There's my most recent navigation, and I just got to say that this is quite possibly the code that I am most proud of so far with Walter. And I'm not saying, but I'm saying, I'm just saying that if Walter was run by a propeller chip, he could be simultaneously doing this and scanning and talking to processing whilst still driving. And because all variables are global, are public variables, the same variables that are being spit out for processing can also be spit out for its onboard navigation. So I can have processing crunching the numbers on what path to go for and to pick the most creative or interesting path. At the same time, Walter is using those same numbers in real time to be avoiding obstacles. So a dog could run in front of Walter and he could see it and stop. At the same time, processing, meanwhile, via Bluetooth, is over here calculating his next pathway. If his pickaxe brains don't actually contain his soul, and if I were to swap out his brain and wouldn't be killing him or stealing his soul from him in doing so. So there you go. Thank God YouTube is up to 15 minutes, or I wouldn't have made it. Ting.